Hi, my name is Mike Archbold.
My name is Brandon Fry.
My name is Devin Pelkey, and
we are the Group 22 UAV team.
Our objective is to develop a UAV for Hatfield Company for military surveying purposes.
This UAV will consist of 3 main blocks. The first block, the GUI interface, is essentially the user interface into the UAV. Devin will be discussing this block later on in this video. The second block, the main processor, acts as the brains of the UAV. Mike will be discussing this block later on in the video as well. The third block is the flight controller. This acts as the muscle for the UAV. I will be discussing this block later as well.
After we finish discussing each block, we will cover the customer requirements given to us by Hatfield Company and a little bit how we are going to meet each one. After that, we will discuss our schedule for the rest of the year of how we intend on completing our UAV project.
This is the block diagram for the graphical user interface portion of the UAV project that is written in C#. First, we have a display console that displays the current latitude, longitude, altitude, land speed, and GPS signal. This information is transmitted from the main processor on the UAV through the XBee using FTDI. It is transmitted into the computer using the USB and then displayed on the console. Here we have the flight plan. The flight plan is where the user inputs the coordinates that they would like the UAV to travel and where to take the pictures. This is the proposed display screen for the graphical user interface portion of the UAV project. Up here at the top we have the latitude, the longitude, the altitude, the speed, and the GPS signal. This is important information for the user because they need to know what's happening at any given point in time. Along with that information, we have status updates on the left-hand side. This includes powering on, ready, in-flight, low battery, and even communication loss. In the case of communication loss, a very large screen would pop up over the top of this and let the user know that something has gone extremely wrong and that they have to acknowledge that something has gone wrong. In the center here, we have a portion for the image. Now this image is being transmitted from the main processor through the XBee onto the screen as described before. Now if there hasn't been an image taken and transmitted yet, this area will remain blank. On the right hand side we have the next location. This is important for the user to understand where the UAV is going and what it's planning on doing at that point. Down here on the lower portion of the screen, we have the flight plan information. So this is where the user would input the coordinate points and altitude for the flight plan, and so this is where the UAV will get all of its coordinates and where it's going and when to come back.
This is the block diagram for the main processor block of the UAV project. First, it uses an Atmel XMEGA128 microcontroller process all the data from these 4 separate modules, as well as send commands to the flight controller block that will be discussed by Brandon Fry in the next portion of this video. The GPS module is used to get the latitude and longitude position within an accuracy of 10 centimeters, as well as the direction, the altitude, and the satellite signal strength in a range of 0 to 12 satellites. After that, the barometric pressure sensor is used to calculate the altitude with the air pressure as well as the temperature of the air in order to get an accurate reading. Once these 2 altitudes have been obtained, they can be cross-referenced and a highly accurate altitude will be the result of greater than 25 feet. Next, the camera module can be used to get a JPEG image of 640 by 480 pixels and can be transmitted wirelessly through the XBee module back to the user interface. Also, the XBee module can be used to send an update to the user interface, which entails the current position, land speed, altitude, and satellite signal strength. In addition to the Zigbee transmitting signals, we can receive the next position in the flight plan, which can then be cross-referenced with our current position of the GPS. Then the direction that we need to go can be calculated, and a command can be sent to the flight controller in order to make that happen.
This is the block diagram for the flight controller. As previously said, the flight controller acts as the muscle for the UAV. It operates by first receiving a maneuver request from the main processor. The flight controller, which utilizes an XMEGA128,
then takes in that request and runs it through a set of algorithms to determine how to position the different motors and servos on the UAV. It controls the motors and servos using PWM, which stands for pulse width modulation. While this is happening, the XMEGA 128 is reading in data from 3 different sensors, 2 of which are accelerometers, and 1 of which is a gyroscope. The 2 accelerometers allow the UAV to determine its orientation relative to the Earth's surface by looking at the linear acceleration due to gravity. The gyroscope, on the other hand, allows the UAV to determine its angular acceleration so that it can see which way it's rolling off and help compensate against any unwanted rolls. What we also see here is the XMEGA 128 utilizes a proximity sensor. This proximity sensor will be mounted on the bottom of the UAV, and it allows us to see what the elevation is anywhere between 0 and 255 inches. This allows the UAV to get a better resolution of its altitude at low altitudes. This will be primarily used during landing sequences where an accurate representation of altitude is required. Hatfield Company gave many requirements when proposing the idea of an affordable UAV for military surveillance. Some of the top requirements listed included portability, long range, the ability for in-flight pictures, customizable flight plans, and reasonable altitude capabilities. To meet these requirements, the following engineering requirements were developed. To meet portability requirements, the UAV must be capable of taking off and landing in an area of 25 square feet. The UAV will meet the long-range requirement by being able to fly and maintain communication in a 0.5-mile radius in urban areas and a 1.5-mile radius in an open area. The UAV will carry a camera module that can take pictures at a resolution of at least 160 by 120 pixels per inch, which allows it to meet the customer requirement of taking in-flight pictures. The user interface will allow the user to make a flight plan and execute it with the UAV meeting the customizable flight plan requirement. To meet the required altitude capabilities, an aircraft with a max altitude of above 100 feet will be chosen.
This schedule represents the plan of action for constructing this unmanned aerial vehicle over a 26-week period. Weeks 1 through 11 represent fall term, weeks 12 through 15 represent winter break, and weeks 16 through 26 represent winter term. Currently, we are at the end of week 7, so far in week 1, we came up with our top-level block diagrams and prototype schematics. Week 2, we researched which parts we needed and ordered them. Week 3, we developed our prototype circuits. Week 4, we designed, routed, and ordered the prototype PCBs. And then in week 5, we began writing the test code to test our prototype PCBs and began interfacing with the modules. Week 6, we plan to take a break for midterms. Week 7, we put a final schematic in pads, began the final code implementation, and set up communication between all 3 blocks in our system. Now during week 8, we plan on laying out, routing, and ordering our final PCBs, continue to implement the final code, and then week 9, we plan on continue to code, wait for the PCBs, and then order the components necessary to stuff the PCBs. Then week 10 and 11, we plan on studying for finals and then taking finals. Over the first week of winter break, which is week 12, we intend on stuffing the PCBs, implementing test code, and then continue the final code implementation. In addition, we want to mount the case on the bottom of the helicopter, mount the flight controller inside of that case, and then during weeks 13 and 14, we are going to take off for Christmas break. We'll come back the last week of Christmas break, which is week 15 on our schedule, continue to implement code until the first week of school, which is week 16. During that week, we will do our first low-altitude system test, which entails having the helicopter autonomously hover off the ground at about a 6-inch altitude. After that, in weeks 17 and 18, we will continue to test modules and then small tests of the helicopter and to continue to fine-tune our code. In week 4 of winter term, which is week 19 of our overall schedule, we will have our first long-range, full-altitude test in Eastern Oregon. That will include going into an altitude of at least 100 feet, flying at least 1.5 miles away from the command center, and then returning to base fully autonomous. On week 5, we will take a break for midterms, and then week 21 through 26, we intend to test, and continue implementing the final code until our helicopter is completed.
So in this video, we discussed the purpose of the UAV project, as well as the 3 block diagrams.
We also discussed the customer requirements as well as the engineering requirements to meet those.
And finally, we discussed our 26-week tentative schedule of how to complete the UAV project.
So this is the Cloudy Shadow team saying,
Stay classy, Oregon State!